Hello everyone, and thank you for joining us for today's webinar. My name is Neil Foley, and I'm the Applications Engineer here at RIZE. Today I'm going to be talking about some different manufacturing technologies and comparing the different degrees of tolerances that you can achieve with each of them. So we're going to touch very lightly on some traditional manufacturing, but primarily this will focus on a few general additive manufacturing technology approaches. So first, I'll talk about sort of what I mean by tolerance. So what I mean when I say engineering tolerance here is a deviation from the target dimension of a given portion of a part that you are trying to produce. So this is specifically the amount that the dimension varies away from what you were aiming at. So there can sometimes be a bit of ambiguity among similar terms, things like tolerance, error, relief, allowance. So I wanted to make the distinction that tolerance is how far you are from the target, whereas something like allowance would be the amount of space that's left, the amount that you deliberately reduce from a given target in order to leave space for a joint, for example. So some of the different things that can contribute to engineering tolerance include tooling limitations. So this could be the result of having a limited resolution in the types of tools you're using, either to add material or remove material. It could also be the result of material limitations, whether that is because the material is composed of units that can't produce a certain shape with a certain precision. It could also be because certain materials are prone to warpage due to various factors. And it could also be the result of limitations in the manufacturing process. Oftentimes, certain manufacturing processes are very effective at producing certain types of geometry and less effective at producing other types. So the more complex the part is, the more likely it is that a given manufacturing it precise tolerance. So here is a quick overview of some general numbers for general manufacturing technologies. So these are sort of middle of the road estimates for the X and Y tolerance based on both the resolution and the precision of these technologies, as well as the Z tolerance. For most of the additive technologies, this would be more based on the vertical resolution as opposed to precision. So for fused filament fabrication, which is one of the perhaps the most common 3D printing technology, it is the generally lowest cost approach and can produce parts that are strong very quickly. So it's a common approach, and it tends to be a little less precise than some of the other methods we'll look at. That's because it takes a filament of thermoplastic and extrudes it into tool pathways onto the build surface, whereas certain other technologies can use more precise methods. So another technology is powder bed fusion. And this can be done either with thermoplastics or with metals or with some other materials. And you tend to be able to get a bit better tolerance with this, although you can also be prone to some warpage that you may not see for certain types of geometry with filament fabrication. Another method is photopolymer curing. This is when you use special resins that under UV light can cure from a liquid state into a solid. And because it can be applied to a build surface as a liquid, you can get very high resolution with this approach. And so you can have quite low tolerances if everything goes well. And finally, Just as a point of comparison, some traditional manufacturing methods sort of fall lower and higher than this range. There are so many different types of manufacturing methods using machining tools for subtractive manufacturing or investment casting or forming or all sorts of things, and each of these can have tolerances with either a very narrow or a very wide range. So I just included that here to sort of illustrate what sort of ranges we're working with for those as well. So now we'll look specifically at fused filament fabrication and the types of things that cause some of the challenges with getting high tolerances, as well as some of the things to improve those. So one of the main challenges to getting precise tolerances with FFF printing is limitations in the X, Y, and Z resolution. So generally you can get quite high X and Y resolution with FFF printing, but it's limited in the sense that you can produce very minor changes in a surface, very fine X and Y changes. However, you can't produce very fine standalone features in X and Y. That's because the extrusion nozzle often has a very high resolution in terms of being able to adjust its path very slightly to one side or the other. However, the path itself is rather wide compared to that resolution. So if you try to produce very narrow features, you'll run into limitations in that sense. Now, the Z resolution is a value that's going to be limited to multiples of a specific number. So because of that, you'll be limited in terms of trying to achieve tolerances that are narrower than the thickness of one of your layers. You won't be able to do that, except with some post-processing methods in some cases that will allow you to reduce, remove material and get closer to the target dimension. So another major challenge that's relevant to tolerancing for filament fabrication printing is thermal contraction. So this is the effect that often causes troubling warping with large parts in thermoplastic 3D printing. So as a part is being printed, the thermoplastic is being heated up very hot to the point of melting or nearly melting, and after it's been placed, it starts to cool down, and depending on the rate at which the material cools down relative to the material that's already on the build or is being applied to it currently, this can create some internal stresses in the part that could eventually pull up at the corners of the part or cause some changes in the geometry. So this is a challenge that can have one of the greatest effects on whether or not you can achieve good tolerances on your 3D printed parts. So later on we'll be talking about some effective ways of reducing thermal contraction to avoid this issue. And finally, one of the things that's unique to fused filament fabrication is toolpath interference. So this is the idea that as toolpaths are being placed and being extruded right up against one another, in some cases it can cause those toolpaths to be pushed outward slightly. And this can either be the infill pressing against the contours, or in a special case, as a contour is being laid down, if it's following a curved line, then the inside of the curve will be receiving more material per distance of its length versus the outside. And this results in that material sort of bunching up and reducing the dimension of the inside surface. So this is something to pay attention to, and this is another thing that in some cases can be solved with software. We'll also look at a way of improving it during the design phase. So another major type of 3D printing is powder bed fusion. As I mentioned, you can use a whole different variety of materials for this, but always you'll be using a very fine powder and using either a laser to melt and join that powder together, or you'll be jetting a binding agent that acts as a sort of glue to hold it together. So in the case of powder bed fusion, the X, Y, and Z resolutions are all essentially dependent on the resolution of either the print heads that are jetting your binding material, or on how narrow of a laser beam can be produced and how practical it can be to reduce the laser beam to such a fine space. So that's one of the limitations on resolution. Another thing that can affect powder bed fusion is warping caused by the other two qualities mentioned here. So in the same way that fused filament fabrication can result in warping due to thermal contraction, powder bed fusion can have the same effect due to the heating up of the part from the laser, and then as it cools, it forms those same internal tolerances that can cause certain portions to contract at different rates and bend it out of shape. Then another effect that is unique to powder bed fusion is air pocket packing. So as each layer of the part is produced, additional powder will be applied to the top of the powder bed, and it gets packed down to ensure that no air pockets will form inside the part and create weak points or cause the part to break as it's printing. But in some cases, this it's not a perfect process, and air pockets can still form, and this results in the part warping slightly as the powder above it gets packed more. And then the last major category of 3D printing I'll discuss here is photopolymer curing. And this takes on several different forms. The two major ones are SLA, wherein a part is built out of a vat of photopolymer resin, and each layer is built using either lasers or a projection of light to cure the material onto a build surface as it gets lifted out of the photopolymer resin. The other method is to jet photopolymer resin onto a build plate and cure it as it builds using UV lights. So both of these, because they're working with a liquid, can achieve quite high degrees of precision because they have such high resolutions both with the print heads and with the lasers that they use. So some of the challenges to producing parts with photopolymer curing with high resolution is particularly for SLA, which is the method in the image shown, where a part is being gradually lifted and cured out of a vat of resin. Some of the challenges are that if you have portions of it that don't have supports attached to them, then it's more likely that those portions will bend as the part gets printed and weight is applied to them. And there are also some photopolymer materials that come out more flexible than rigid, and those can also succumb to some bending as they build, which will produce warped geometries and not quite what was specified. So one of the other major effects on photopolymers that can significantly affect tolerances is the effect of post-curing. So as these parts are built, UV light is applied to them to cure them from a liquid to a solid. However, it generally doesn't fully cure the material, and if those parts are then exposed to UV light, or in some cases just heat, or maybe even other chemical processes like high humidity in the air, then they can continue to cure primarily on the surface, and this can also cause them to warp out of shape. So that's something, if you do plan on using photopolymer curing, you'll have to pay attention to, making sure that if you want parts to last for a long duration, you'll have to keep them in an environment where they're protected from those heat and chemical effects. So now I'll talk about some of the best practices for these different 3D printing approaches. and how to deal with some of the issues that I've already mentioned. So one of the first ones that is relevant both to filament extrusion as well as powder bed fusion is, of course, avoiding thermal contraction. So there are some different ways to do this. There's a lot of documentation about how to do it well. So one of the ways is to orient your parts in some different ways to ensure that as they're built, the internal stresses are not able to build up as much as they would in a less ideal orientation. So oftentimes orienting a part to be standing upright, make it taller, or orienting it to have less bulk near the bottom of the part can help to improve the situation. Another thing to pay attention to is the materials being used. Certain materials are more prone to thermal contraction than others, and especially if you're working with a large part that needs tight tolerances, it's important to choose the proper material for dealing with that. And finally, it's important to make sure that as you design these parts, you're using an additive approach if you intend to produce them with additive manufacturing, because in some cases, a part that was designed for subtractive manufacturing may have a lot of bulk on it because it's inefficient to remove that bulk if it's not necessary when you are using a method that removes material from a stock rather than adding material to a build plate. Because of that, when these types of parts are transferred over for production with additive manufacturing, they can often have a lot of extra bulk, which creates this problem of thermal contraction, and also has some other negative effects like increasing the print time and things like that. So the next point I have here is to avoid post-curing. I spoke a bit about this on the last slide. Essentially, this is just a point to, in order to ensure the longevity of photopolymer resin parts, you'll want to make sure that they are insulated from UV light exposure to some degree, as well as avoiding high temperatures or high moisture environments. Another thing that's valuable when trying to ensure you get good tolerances on your parts is being aware of the machinability of the different materials you're working with. So oftentimes fused filament fabrication parts can be quite effective for being machined for reworking any tolerances that need to be adjusted. Our Rizium material, both Rizium 1 and Rizium Carbon, are very effective for this purpose. They machine very well. Photopolymer cured resins can also in some cases be very good for machining. They tend to be a softer material, which can make them easier to machine, but can also in some cases make them weaker. And then for powder bed fusion, it will depend somewhat on the material you're using. That method can sometimes create more brittle parts, so it will not really be an appropriate material or process to use if you choose to rework parts, but some materials are all right to use for that purpose. Another thing to pay attention to is not just the tolerance of individual dimensions, but tolerance stack up, where if you measure tolerance from one datum and then use the next surface as a new datum, then you may find that part larger dimensions are becoming more out of spec than intended. And so one thing that you can do to avoid this is make sure that each dimension is isolated as well as possible. And there's plenty of documentation on how to avoid tolerance stack up and how to deal with it. Now, the final point I have here is called iterative remodeling. And this is, in some sense, a total solution to having issues of tolerance for things like thermal contraction and certain other issues that we've mentioned here earlier. And this is a solution that will not reduce the range of the tolerance that you're getting when you produce a part, but it will reduce the average tolerance so that any variation in the dimension of the part will still be centered around the target. And that can in many cases help bring parts within spec. So I'm going to do a quick demo on what I mean by iterative remodeling, and just show how to then implement that in software. So essentially, what I mean when I say iterative remodeling is initially you will design a part to the dimensional specifications you desire, and then once the part has been produced, it's been 3D printed, then you will measure the part using your calipers. And once you have identified the variation of each dimension from its target, then there are some pretty quick ways that you can then apply that in software to get the model closer, or get the produced part closer to the intended specifications of the model. So I have SolidWorks right here. Oh, lost it. All right, so here is a fairly simple part, and you can see that it has various dimensions applied to it. Each of these lines has some dimension applied and presumably some tolerance associated with it. This has additional ones. So essentially what you would do to use this iterative remodeling approach would be, after the part has been produced, you then measure all of the dimensions that you care about being accurate and record the variation of each of those from the intended dimension. And then what you can do is go over to this configurations tab, and initially what you would do is go to insert tables and create a design table. And I've already done that here. And what a design table essentially does is it gives you the ability to create different configurations and very easily change the dimensions of the part for each of those configurations. So I'm going to open up this table. And it's coming. All right. So here we have our default configuration, and here are all of the dimensions of, or here are all the intended values of all of our dimensions. So these dimensions are not specifically named, they each just have a number and a sketch reference. But to make this easier, it's good to actually change these numbers so that you'll recognize what's intended by, or what's referenced by each of those numbers. So then what you'll do is you will pick a row. You'll want one out of the way down here, and you just input the variation for each of these dimensions. So for example, if this was 0.1 and this was minus 0.2, and there we go, minus 0.2. Doesn't have enough room to show it, but keep going, and let's say this is bigger, 3 and 4 and 0.5, and then I'll make the rest just 0.1. Then once you have all of those filled in, and again, you don't necessarily have to do this for every dimension, just the ones that you care about getting within specification, then what you can do is create a new configuration. So I will call this one corrected 1. So this is our first iterated configuration with some adjustments, and then what I'll do is say that this will be equal to the intended dimension minus the error that we got from that. And then I drag this through, and that creates all our new numbers. So if I were then to create a second iteration, I could add another row of errors in this row here, and then I could just drag this whole row down, and it would fill in the next one, and I would give it a new name. So once I've done this, then when I close out of this design worksheet, it generates a new configuration with the name I gave it. And now I can actually select this configuration, and it will adjust all of the dimensions for me. And so from there, it's as simple as saving your part as the appropriate file type. In our case, you can simply go to this tab and export to RIZE, and it'll pull it up right away. And This allows you to very easily track and make iterative adjustments to zero in your tolerances without having to change the original design of the part. So I can still go back to the original intended dimensions and have the precise model shown right here. So I believe that's all I have for this demo. So I'm going to go back in here. And then besides that, I just wanted to quickly talk about some of the other differences among 3D printing technologies aside from tolerancing, because there's a lot of variety, not only from one general technology to another, but even within, for example, fused filament fabrication. There's a lot of variation from one machine to another, and that's the case also for resin curing and powder bed fusion. So I'll just go through these pretty quickly. So strength is very material dependent. You'll find that technologies that can produce parts in metal are of course going to have the highest strength. Beyond that, it's really what sorts of materials can be processed effectively with the different methods. So you'll find that fused filament fabrication can create quite strong parts. Oftentimes you'll find delamination in fused filament fabrication parts. With RIZE materials, that's not quite as much the case. Our Z-axis is about 90% as strong as our X and Y axes, so you tend to not run into nearly as much delamination as comparable technologies. Another thing is surface finish. So surface finish is in many cases closely tied to tolerance or resolution. So the resin printers are going to have very good surface finish. The powder bed fusion types of technologies are going to generally come in second, and fused filament fabrication usually has the lowest resolution, so it's going to have usually the lowest surface finish. However, there are some special cases in even fused filament fabrication that can get very good quality surface finishes, especially on surfaces that are oriented in the right ways. And there are some post-processing methods that can improve it as well, but that will just be something you'll have to decide whether you want to put in that extra time and effort. Another question is geometric complexity. Each of these technologies is really good at producing a certain subset of geometric complexities. Generally, all of these, any 3D printing method is going to be more effective at really complex or organic surfaces than a traditional manufacturing method. Traditional manufacturing methods tend to be better with square or conical types of surfaces. They have more trouble with generatively produced surfaces and things like that. But any 3D printing method can deal with those quite well. Some other things to look at are print time and post-processing time. In our case, due to the specialties of RIZE and RIZE 1 technology, we are able to bring the post-processing time very low because we're able to jet a release agent between support and model material so that supports can just break right off and the part can be ready often within a few minutes or even a few seconds. Another question is safety. This often comes down to the materials involved. Photopolymer resins tend to be fairly chemically hazardous, so you'll have to be careful when working with those. Powder bed fusion can also be a bit dangerous due to the possibility of catching fire and even explosions due to aerosolized powder. Fused filament fabrication can also often be dangerous in terms of air quality. Most fused filament printers are going to be emitting all sorts of harmful chemicals as they print due to decomposition of the material that they're using. In our case, the RIZE materials do not decompose at the temperature that we extrude at. So there's actually zero emission of volatile organic compounds from RIZE machines. and we actually just got certified by UL for 3D printing emissions safety certification. And then finally, there are questions of ease of use and cost, and these are very much going to vary quite a bit from one machine to another, even within the range of various technologies within 3D printing. So cost can vary quite a bit based on whether it's more of a hobby machine or an industrial machine, as well as the quality of the parts you can get in general, and ease of use is going to vary quite a bit based on the sort of user interface that was created and whether it's intended for beginner or expert users. So that's all that I have for this webinar. I'm going to stick around for a few minutes if anyone has questions. So thank you all for joining our webinar. If you have any questions, you can type them into the chat window and I'll stick around for a few minutes to answer them. Otherwise, if you have any unrelated questions or just want to reach out and get more information, you can always reach me at applications@rize3d.com. Thank you very much.